We'll wait for a few more minutes and then we'll begin. Hello everyone, this is Tanya. I'm one of the TAs assigned to the Aircraft Stability and Control course taught by Professor A.K. Ghosh. So we've gone over 12 weeks of content of the course, and now we'll go over the concepts briefly as a revision to your exams. So before that, we'll also discuss the assignment questions of week 12. That is in fact tutorial sessions that help you revise the concept that we have studied throughout the course. So the entire session would be something like a revision. Okay, so let's initially start with the revision. Okay, so what was static stability? This is the first thing that we started this course with. We defined what is stability, what is static stability, and then we moved on to dynamic stability in the second half of the course. Okay, so what was static stability? Can someone tell me what was static stability? It is written right there, an initial tendency to go back to equilibrium. So for an aircraft, what was it? Static stability is the initial tendency to go back to equilibrium. How did we define it for an aircraft? Can someone tell me? We initially started with longitudinal static stability. Can you tell me how that was defined? Just the definition of static stability is given there, just apply it to longitudinal static stability, the longitudinal stability of the aircraft. No? Okay. So when the aircraft is flying at trim, what is trim? Trim is written in the third point of the slide. So this is trim. Just a minute. Trim is when the net forces and net moments are equal to 0. Summation of all forces, summation of all moments, they're equal to 0. That is trim. Right? Okay. So when the aircraft is flying at trim and you disturb it from this equilibrium point, its initial tendency to come back to the trim condition is defined as the static stability for an aircraft. Okay. So then we discuss concepts of like aerodynamic center. So aerodynamic center is the point about which Cm is independent of angle of attack. So we know our forces are concentrated at a point, our aerodynamic forces are concentrated at a point called Cp, center of pressure. What is center of pressure? So if you have, this is your airfoil, and if it's flying with some angle of attack, you have, just a minute, yeah. So you have your pressure distribution something like this, wait here, something like this, okay, where you have negative pressure gradient above this on the upper surface and positive pressure gradient below the surface, which is what generates lift, right? Okay, so the centroid or the point at which this force effectively acts is called center of pressure. Now when you change the angle of attack, the center of pressure either moves forward or behind depending on whether you increase or decrease your angle of attack. Okay, so throughout your flight duration, since your angle of attack keeps changing, your center of pressure keeps changing. So it becomes difficult to perform the analysis about such a point because it's changing continuously. So what do? You find a point that remains fixed. Such a point is the aerodynamic center. So aerodynamic center is a point about which the pitching moment or Cm is independent of angle of attack. So when you transfer the forces from the center of pressure to the aerodynamic center, it comes along with a moment. What is that? That is the Cm naught. Cm naught or Cm of the wing, right? So Cm alpha, Cm naught of the wing. Okay, so that is that quantity. So when you, if this is your center of pressure, this is your aerodynamic center. Okay, let me just draw another. Okay, yeah. If this was your center of pressure and this is your aerodynamic center, the lift and drag were initially acting at Cp, and then you transfer it to your aerodynamic center. So now it has lift and drag and it also comes with a moment. So that is CMAC of wing. Okay. So what was the CMAC for a symmetric, cambered, all those different kinds of airfoils? What was the CMAC? CMAC for symmetric, for cambered, for reflex. Before that, what was reflex airfoil? Or can you just go about defining what is symmetric, how is cambered different from symmetric, and then what is reflex? How is a symmetric airfoil different from a cambered airfoil? How is a symmetric airfoil different from a cambered airfoil? Shape-wise or some properties, something. Refer to your notes we had discussed in the first one, I think the first week or the second week. In one of those first 3 weeks, we had discussed this. We had discussed this even after that. So, what is symmetric? What is cambered? How is it different? Why do we need reflex? Where is reflex used? Just refer to your notes or the previous slides or anything that you've taken down. Okay, let's start with the shape. Okay, so symmetric airfoil has the upper and lower surface same. The cambered airfoil will be something like this. So what is the reflexed airfoil? Here, let me see. Okay, let me just erase this. Okay, here you have CL is CL naught plus CL alpha into alpha. So what is CL naught in the case of symmetric airfoil? This was your lift curve slope. CL versus alpha. Okay, I'll draw it for each case. CL versus alpha. For symmetric airfoil, how will it look? First of all, the slope is positive. CL alpha is positive, right? So it will be a positive slope. What is CL naught for the case of symmetric airfoil? CL naught is 0, right? For a symmetric airfoil. So the slope will be, the curve will be something like this. What about for a cambered airfoil? CL naught is, and how will the CL versus alpha look? CL naught is for a cambered airfoil. What is CL naught for a cambered airfoil? For symmetric, it is 0. For cambered, what will it be? Should be greater than 0, right? Because it produces lift even at 0 angle of attack. So how will your curve look? Look something like this. This is your CL naught, right? For a reflex airfoil, how is the shape? So you have an upward curvature towards the tail. So it's something like this. Okay, let me just draw this again. Yeah, something like this is an upward curvature towards the tail. So can someone tell me why this is done? Why did we have to introduce reflex airfoil? Okay, maybe going through the points in the slide will help you. Let's continue. We had stopped at trim. So the pitching moment convention that we had seen for the case for this longitudinal stability is that nose up is positive, nose down is negative, right? Nose up is positive, nose down is negative. How did we get that? Put your thumb, it's the right hand thumb rule. So put your thumb along the longitudinal axis, right? And curl your fingers. The direction of the curl is the positive moment, positive motion. So what is the longitudinal axis? The axis under consideration here, you're pitching about your y-axis, right? So y-axis is towards the wing. Let me try drawing that. So if this is your aircraft, you have a wing here, wing here. So this is your y-axis. This is your x-axis and downward is your z-axis. So if you point your finger along the y-axis, the direction of the curl of the fingers is the moment in that direction, right? So nose up is positive, okay? Yeah. Then we had seen the linearized version for the pitching moment coefficient Cm was Cm naught plus Cm alpha into alpha. And we had seen that the only condition for longitudinal static stability is that Cm alpha should be less than 0. Another condition that we saw is Cm naught should be greater than 0. This is in no way related to stability. We require or we prefer Cm naught to be positive because we wish to trim our aircrafts at positive angles of attack. Okay, it is not related to stability at all. The only condition for longitudinal static stability is that Cm alpha should be less than 0. So what does the curve look like? If this is Cm and this is alpha, how should the curve look like? Like this, right? With a positive Cm naught and a negative slope. Now, how do you ensure positive Cm naught? Maybe this will help you answer some other question that we started with in the slide. How do you ensure Cm naught is greater than 0? Because when you transfer the forces from, I erased that, okay, from Cp to Ac, it comes with a nose down moment, right? So if this is something like this, Cp, this is AC and you have lift and drag. When you transfer it to AC, it comes with a nose down moment. Your CMAC is less than 0, correct? So your Cm naught for the entire wing would not be greater than 0. How do you ensure Cm naught to be greater than 0? How do you do this? This I remember that we had discussed extensively during 3 weeks, first 3 weeks. I think this question was posed in the first week discussion and then we had answered it in the second and third weeks and we had discussed this extensively. Can someone tell me how to ensure Cm naught is greater than 0? Refer to your notes, check out the previous slides and let me know. How do you ensure Cm naught is greater than 0? Refer to the slides in week 2 or week 3. I think we discussed it there, the answer to this question. Why do we need Cm naught to be positive? To trim at a positive angle of attack. Okay, how do we ensure Cm naught to be positive? One way is the reflexed airfoil. How does it ensure Cm naught is positive? How does it do that? I think we discussed two ways, right? One way was the reflexed airfoil. Now that we have drawn the reflex airfoil there, can you try and tell me how reflex airfoil ensures Cm naught or CMAC is positive? Or can you tell me another way how to ensure Cm naught is positive other than reflex airfoil? So if you add a tail to this wing configuration on the aircraft, that would also contribute to some Cm naught or Cm alpha, right? So if you set your tail in such a way that it compensates for this negative Cm naught, you will get compensates and overcomes the negative Cm naught, you will get a positive Cm naught. Okay, so you arrange the tail setting and the wing setting angle such that you can get a positive Cm naught. Now let's come back to the original question. How does the reflex airfoil ensure that Cm naught is positive? So there's an upward curvature towards the tail, right? So what it does is that the CP either moves ahead or coincides with the AC. So CP is here and AC is here. So now when you transfer the forces, it comes with a nose up CMAC, right? So this gives you a positive Cm naught. Okay? Okay, let's go on to the next slide. Yeah, so this is the wing contribution towards Cm at the CG. So the wing contribution is CMAC wing. CMAC wing is what we just, okay, the slides have been updated. Yeah. So the wing contribution again has Cm naught plus Cm alpha into alpha. We split it in such a way and write the equation like that. Okay. So your Cm naught contributors, this entire thing is Cm naught. Okay. Then you have, this is Cm alpha. So our equation becomes Cm naught plus Cm alpha into alpha. Okay. Yeah. Now see the second point, it says for static stability, AC, aerodynamic center, should be aft of the CG. But when this happens, what happens to your Cm naught? Your Cm naught becomes negative, which is not something we desire. If this, oh, just a minute. Yeah, if you require Cm naught, 1 minute. If you require Cm naught to be less than 0, what we need is that the AC should be should be aft of the CG. But when you do that, your Cm naught becomes less than 0. So what do? You add a tail, right? This is what we discussed in the first slide. So this is the tail contribution. Now this is your Cm naught tail, this is Cm naught wing, and this entire thing is your Cm alpha of the tail. Alright, so here you adjust your tail setting angle and wing setting angle such that your Cm naught tail becomes a positive and more positive, so that it overcomes the negative Cm naught of the wing. Okay, so for that what do? You ensure I tail is less than 0, that's one way, or I wing, that's the wing setting angle, is greater than the tail setting angle. So IT is the tail setting angle, IW is the wing setting angle. Okay, so two ways to ensure positive Cm naught is to make tail setting angle less than 0 or the wing setting angle greater than the tail setting angle. Okay, next we saw a concept known as neutral point. Now till we had the wing, we only needed aerodynamic center. When we added the tail, another surface was added onto the aircraft which has another aerodynamic center. So we have to come up with a new point to analyze the stability. That point is neutral point. So aerodynamic center of a wing is equal to neutral point of a aircraft. Okay, so it's defined in the same way. So neutral point is the CG location at which Cm alpha is 0. It's independent of angle of attack. The pitching moment is independent of angle of attack. Same definition as the aerodynamic center. Then we derive the equation for the neutral point location, right? So now if you add some other surfaces, so this XAC of the wing, and then you added a tail, so you pulled the aerodynamic center backwards. Now if you add a canard, you will have some negative surface, negative quantity here, right? So you may have volume ratio of the canard, efficiency factor of the canard, then you might have CL alpha canard by CL alpha wing, and this downwash component is not there because the canard will be ahead of your wing, right? So it's not downwash. What was downwash? We discussed this even in the last week, that is the week 12 session. We discussed this even there. What was downwash? Downwash is represented by epsilon. That epsilon naught plus 2 epsilon by d epsilon by d alpha into alpha. So what was this epsilon downwash? What was epsilon? How do you define downwash? What is downwash? What does it do? What effect does it have? So this is your aircraft, right? And you have a wing here, you have the tail here. Wing is longer than the tail. Okay. So now, when imagine another view of the aircraft where the flow from below the surface of the wing interacts with the upper surface flow of air above the surface of the wing. The point at which it interacts, both the velocities coincide and you have some vortices generated. Now these vortices travel downstream towards the tail. This effect is known as downwash. Right? What does downwash do? What effect does it have? It reduces the effective angle of attack at the tail. So what does downwash do? Reduces angle of attack at the tail, reduces the velocity at the tail. So the oncoming velocity, free stream velocity seen at the wing is different from the free stream velocity that the tail sees because of these vortices, because the tail is in the wake of the wing, right? So this is what downwash is, this is the effect it has. Okay, so that's why I said the canard will not be affected by downwash because it's not in the wake of the wing, it's ahead of the wing. Okay, so you'll have such terms added when new surfaces are added onto the aircraft. Okay, then we saw static margin. What is static margin? Yes, it's the difference between the neutral point location and the CG location. It's also the negative of the DCM upon DCL, the slope. What is static margin? It's the equation is given here, but how do you define it? What is static margin? What does it tell you? What does static margin tell you? It's a measure of what? Which measure of stability? Yes. So for a statically stable aircraft, will the static margin be positive, negative, zero? What will it be? For a statically stable aircraft, what will your static margin be? It will be positive, right? Static margin will be positive for statically stable aircraft. So that means your DCM, we know this, CM versus CL graph will have a negative slope, just like the CM versus angle of attack, alpha. Okay, all right. Another thing that we had seen was, where do I show this? Okay, so your CM versus alpha, this it has the same nature. Both these graphs, CM versus CL, CM versus alpha, will be of the same nature. What does that mean? It will both have a negative slope. Okay, but these CM naught or the intercepts of both the graphs are different. We had done one question on this in week 2 or 3 again, where this question was asked. You need to remember that both these intercepts are different. They're not the same value. They will be same only in the case of a symmetric airfoil. Okay, But for other kinds of airfoil, other cambered airfoils, reflex airfoil, or any other shape, these two intercepts will not be the same. Okay, so please keep that in mind while solving the questions. The two intercepts are not the same. Cm naught is this value. This is Cm naught. This is not Cm naught. Correct? Cm naught is the y-intercept of the Cm versus alpha curve, not the Cm versus Cl, although it follows the similar pattern. Okay, it is the same only for a symmetric airfoil. Alright, let's go to the next slide. Yeah, then we had seen how the downwash, epsilon naught, and the slopes are defined. We'd seen the volume ratio of the horizontal tail, right, where LT is the moment arm, that is the difference between the AC of the tail and the CG of the aircraft. Okay, then we had seen that the CL alpha 2D, that is CL alpha for an airfoil, is different from the CL alpha of a wing. Why? Can someone tell me why CL alpha 3D is not equal to CL alpha 2D? The formula is given here, so you know it's not equal, but why? Physically, can you tell me why it's not equal? Just tell me what's the difference between an airfoil and a wing. Then you'll be able to answer this question. From the formula, can you tell me if CL alpha 3D is greater or less than CL alpha 2D? Is it greater or less than? What is it? It's less than CL alpha 2D, right? So this is wrong. So CL alpha 3D is less than CL alpha 2D. Okay, that is right. Can you tell me why? Physically, why? How is a 2D airfoil different from a 3D wing? Physically, how is it different? We had seen one question where they asked the effect of aspect ratio on CL, right? Remember that? We'd drawn the graphs. Does that give you a clue? Okay, so do you remember this graph CL versus alpha? So it was like this. This was for aspect ratio, say 5, 10, infinite. What does infinite aspect ratio mean? What was the formula for aspect ratio? B square by S. Yes? Where B is the span and S is the weighted surface area. So for an infinite aspect ratio, what else would be infinite? Span, right? So that means B is infinite. So infinite span is something that's associated with the airfoil. So airfoil is a wing of infinite span, whereas a wing has a finite span, right? So when the flow, just that we just discussed this in the previous section, the vortices. So when the flow below the surface of the wing interacts with the flow above the surface of the wing, you have vortices formed. And this leads to a reduction in the lift that the airfoil was producing. What the lift that the airfoil could actually produce is reduced due to the wingtip vortices, right? This is why the CL alpha 3D is different from CL alpha 2D. Okay? Okay. Another thing that you remember here is all of these formulae, this one and this one, are valid only in radians or per radians. Okay, so those equations, the CL alpha 2Ds, yeah, so the CL alpha 2D and all of that is valid only when uh, this entire equation, CL alpha 3D equation, dou epsilon by dou alpha equation is valid only when CL alpha is given in per radians. Okay, and the answer that you get, if it's degrees, it will be radians or per radians, vice versa. Okay, okay, so let's move on. Yeah, then we introduce controls. What do controls do? It does not affect stability, right? Changing the control in any way does not affect stability. This question has been repeated multiple times, so be careful that control surfaces have no effect on stability. So if they ask you a question like, if I deflect the elevator this much by some 5 degrees, how much will the stability change? It will not change. Deflection of the elevator or deflection of any control surface has no effect on static stability, right? It's a completely different concept. So what does control do? What can you accomplish with it? Why do we need control? Why do we have control surfaces? The answers are given on the slides. Can you tell me? Why do we need control surfaces? It's given there to trim at different CLs, correct? So if your CM versus CL is something like this is your CL trim, correct? When the moment, pitching moment becomes 0, that is your CL trim. So this was your CL trim. So now you want to trim your aircraft at some other CL, say at this CL. You want that to be your new CL trim. What do? You have to move your graph. You just have to translate it. Like I said, it does not change the slope value. What does that mean? It does not affect stability. So control surfaces just translate the graph, the CM versus CL graph, it just translates. What does that mean? Your intercept changes. CM naught changes, not the CM naught of the CM versus alpha. The intercept changes, correct? So control surfaces translate the CM versus CL graph so that you can trim at a different CL while maintaining stability. The stability does not change. Stability of the aircraft does not change at all, right? Because the slope is the same. The magnitude of the slope, the value of the slope is the same. Slope does not change at all. Only thing that changes is the intercept. Okay. So control surfaces are used to trim the aircrafts at different CLs. Then we saw the convention. The convention that we follow is that the elevator down, deflection downwards is considered positive. Okay, downward deflection of elevator is considered positive. So when you deflect the elevator down, what happens? What do you think will happen? So this is your fuselage reference line. This is your wing. This is your tail and CG. Okay, so if I deflect the elevator down, tell me what happens. Just guide me through the entire process. What from starting deflection of the elevator downwards, what does it first do? Just guide me through the process. Deflection of elevator downwards, what does it do? Does it change stability? No, right? We just saw that does not change the stability. What does it do in terms of the aerodynamic forces, lift generation, moments, aerodynamic moments, pitching moment, anything? Just guide me through the process. What does it do if I deflect the elevator down? If I deflect some surface on an aerodynamic surface, if I deflect it down, does the camber change? Yes. So the tail, which is typically a symmetric airfoil, when I deflect the elevator down, it kind of behaves like a cambered airfoil. So how is the cambered airfoil different from a symmetric airfoil? We just discussed this. How is it different? How is it different? It produces lift even at zero angle of attack, right? So when I deflect the elevator down, there is a increase in lift production. So there is a delta L. Okay. So what kind of moment does this produce at the CG? Pitch up, pitch down. What does it do? it produces nose down moment, right? It's very visible from this. So it produces nose down. This is what happens when you deflect your elevator down. Okay. Now, since we saw if I deflect my elevator down, which is positive, it produces a positive change in lift. So your CL delta E, that is dCl by d delta E, is positive. Now deflection of elevator down, positive elevator deflection, gives you a nose down pitching moment, right? So that's negative. According to a sign convention, it is negative. So positive deflection of elevator gives you negative pitching moment, which is why your Cm delta E is negative. Cm delta E is dCm by d delta E, which is negative. Okay. Then what is tau? This dou alpha tail by dou delta E. What is tau? What is this? How is it defined? What is that quantity? Tau. Tau is control surface effectiveness parameter, right? So it is control surface effectiveness parameter. Okay. Then we saw this equation, that is delta E trim. That is how much delta E needs to be deflected to trim at some given CL. Okay. So what is the nature of this graph? Look at the quantities in the equation and tell me. So this is delta ECL trim. Oh, sorry, it's the other way around. Just a minute. Oops. Okay. So let me just cut this. This is CL and this is delta E. Okay, tell me the nature of this graph. Positive, negative slope or positive y-intercept. Just tell me. Okay, let's look at the intercept. Okay, so this is the intercept. Is this positive or negative? For a conventional aircraft, is it positive or negative? This is positive, right? So Cm naught is positive, Cm delta E is negative, and you have a negative sign. So the entire term is positive. So your intercept is positive. Fine. Now slope. This term, is it positive or negative? Numerator, x bar np minus x bar cg for a stable aircraft, positive or negative? Positive. Cm delta E, positive or negative? Negative. So what is the slope? The overall term is negative, right? So you have an equation, graph of this nature. Alright? Okay, let's move on to the next slide. Then we moved, this was longitudinal stability control till now. Now we'll look at directional stability and control. First we start with the convention. So the right wing backwards, the right wing moving backwards or yawing backwards is called positive yawing moment. Again, how did we decide this? Put your thumb along the yawing axis, which is the yawing axis? Z, right? So put your thumb along that axis, and the direction of the curl of your fingers is the positive yawing moment. Alright? So the positive yawing moment is your right wing going backwards. Okay? Then the convention for the side slip angle. The relative velocity vector, when it's towards the right, it is a positive side slip. What does that mean? So this was your fuselage reference line, and if your relative velocity is coming from the right, this is positive beta. This is V infinity or V relative, and this is your fuselage reference line. Okay, this is considered positive beta. Then the deflection of the control surface, convention for that. Rudder deflection towards the left is considered positive delta R. Okay, so if I deflect my rudder towards the left, can you tell me what changes in forces and moments happen if this is the CG? Just tell me. So this is your positive y-axis, right? Now can you tell me what kind of forces that if I deflect my rudder to the left, what kind of forces and moments does it produce? Deflection of rudder to the left produces what kinds of forces and moments? We did this for the positive elevator deflection, right? Now let's just try doing it for the positive rudder deflection. Positive deflection of the rudder, that is the left deflection of rudder, what changes does it do to forces and moments? That's the yawing moment and the force in the y direction. Previous case you had the force in the lift direction, right? Here it will be in the y direction and moments along the yawing axis, that is the z axis. Okay, if I deflect my rudder towards the left, I have a force produced in which direction? In the positive y or the negative y? have force produced here, right? So I have Fy positive, right? Does that produce a positive yawing moment or negative yawing moment? Cn. Negative yawing moment, right? Okay. Okay, now let's see for static directional stability, what is the condition required? We require Cn beta to be positive. What is Cn beta? dCn by d beta. So let's see, if the aircraft is subject to a positive side slip, how do you negate it? Like if the aircraft is statically stable, so it should show a tendency to go back to equilibrium. So what is the moment tendency that we should have? What is the restoring moment that we should have such that the positive beta effect is negated? We should have a positive yawing moment, right? So if your aircraft goes this way, then you will not have this side slip angle beta, right? So if the aircraft is subjected to a positive side slip angle, its restoring moment should be a positive yawing moment. That is why your dCn by d beta should be positive in order to maintain, in order for the aircraft to have static directional stability. Okay, restoring moment should be a positive yaw. When there is a positive side slip angle, the restoring moment should be a positive yaw. Okay. Okay. Now, induced beta positive produces what kind of force on the rudder, on the aircraft? Produces force in the negative y direction, right? In the negative y direction, there is a force in this direction. The positive beta produces force in the negative y direction, which is why your Cy beta, this dCy by d beta is negative. Positive side slip produces negative force in the y direction. Okay, so your Cy beta is negative. Okay. Okay, and your Cn beta would be, we require it to be positive. So why is there a negative sign here? Can someone tell me? Negative sign on Cn or Cn beta. Why is there a negative sign? We require Cn beta to be positive. So why is there a negative sign? Why is there a negative sign? Because your Cy beta is negative. Right? This quantity is negative, which is why you have a negative sign to make sure that Cn beta is positive. Alright? Okay. So now what structures what structures on the aircraft contribute towards positive directional stability? It's the vertical tail and the swept wing. Both these quantities have a Cn beta positive. So they are stabilizing structures. Okay, remember that. Remember the sign conventions. Remember the derivatives sign. You can easily find out the sign of the derivatives by just seeing the physical effects it has. Okay, so you don't need to memorize them. Just try to see what effects each of those each of those terms has. So if there is a positive beta, does it produce positive force or negative force? Does it produce positive yawing moment or negative yawing moment? Just try drawing it and you'll be able to get it. Okay. Okay. Next you have the control aspect. Okay. Control aspect. Now positive rudder deflection we had seen is rudder to the left. Okay. It produces a negative yawing moment. We just saw that, right? See here. If I deflect my rudder to the left, it produces Fy in this direction, which produces negative yawing moment. Correct? Okay. Which is why your Cn delta R, which is dCn by d delta R, should be less than 0. For a positive rudder deflection, you have a negative yawing moment. So it is negative. Okay. Now similar to the elevator effectiveness parameter, you have a rudder effectiveness parameter here. Okay, so that is again denoted by tau, control surface effectiveness parameter. Alright, So now the formula for C and delta R is given. C and delta R we know is less than 0, and all these quantities, so this is positive, tau is positive, only this is less than 0, hence the entire term is less than 0. Okay, now just a comparison between the longitudinal and directional cases. For static stability, in the longitudinal case you had Cm alpha less than 0. In the directional case you have Cn beta greater than 0. At trim, you wanted to trim at positive angles of attack, so your Cm naught needed to be positive. Now we generally prefer trimming the aircraft in the directional sense at beta equal to 0. So your Cn naught is 0. Okay, you don't need it to be positive. So we trim at 0 angle of attack, 0 beta, so your Cn naught is 0. Then the control, Cm delta E is negative and Cn delta R positive. Cn delta R we just saw why it's negative. Why is Cm delta E also negative? What happens when I deflect the elevator down? We had just seen this. Can you tell me again now? Just to refresh our memories, can you tell me? If I deflect my elevator down, it produces a increased lift, positive lift. That produces a negative pitching moment, that is nose down moment at the CG. Okay, which is why Cm delta E is less than 0. Okay, let's go move on. Okay, now let's look at lateral stability and control. Okay, so the conventions here, right wing down is considered positive roll. So again, you put your thumb along your roll axis, which is the x-axis, and the direction of curling of your fingers gives you the positive moment. Okay, so the right wing down is the positive roll, and what else? It's the right aileron up, left aileron down. That again gives you a positive rolling moment. Okay, so these are the sign conventions. Right aileron up, left aileron down. What does it do? If I deflect my right aileron up, will the lift, let me just draw this. So if I deflect, this is right and this is left. If I deflect my right aileron up, does it give an increase in lift or reduction in lift? It gives reduction in lift, less lift, and this gives you more lift. So it rolls in this direction, rolls with the right wing going down, which is the positive roll. Okay, so this is the positive aileron deflection. Okay, now for static lateral stability, you require CL to be less than 0. Okay, so for the stability, the condition that we have is CL beta should be less than 0. Okay, this you must remember, it's only when the vertical tail is above the fuselage reference line, not when it's below. Okay, so the equation for CL beta is given here, and since we know that Cy beta is negative, all other terms being positive, the entire CL beta is less than 0, which is what we require. Now what components contribute towards lateral stability? Vertical tail, high wing, and if it is a low wing, the dihedral angle contributes towards lateral stability. Okay, now let's look at the hinge moment. This was, I think we started this in week 5 or week 6. What is the hinge moment? Hinge is the hinge line about which the elevator is fixed. Okay, so the hinge moment is given by that equation where CE is the elevator chord, SE is the elevator vertex surface, and CH is the hinge moment coefficient. Okay, the hinge moment coefficient again is linearized in this equation. right? Where it's dependent on angle of attack at tail, delta E and delta T. What is delta T? What is delta T? Trim tab deflection, right? So this point, CH alpha tail, CH delta E, CH delta T, they are all less than 0. How we can see this? Okay, so if this is my tail, now if it is subject to increased angle of attack, produces more lift. If this is the hinge line, produces nose down moment, so it is negative moment. Okay, now if I deflect my elevator downwards, it's something like this. Again, lift is increased, you have delta L. If this is the hinge point, it produces nose down moment, negative moment. Similarly, if I deflect my trim tab down, it produces an increase in lift, which produces a nose down moment at the hinge point, which is why all three parameters are less than 0. Okay. Then we saw delta E float. Okay, so it's the angle at which the elevator will freely float if you let go of the stick, right? Yeah, so that is delta E float. How do you ensure delta E float is 0? One way is that CH alpha tail should be 0. For that, what do we need? You need your CP and hinge at the same point. That is one method to ensure delta E float is 0. If your CP and hinge are at the same point, the forces generated on the elevator will be acting at the hinge and hence it will not have any hinge moment. Okay. Another thing is the horn balance. What was the horn balance? If this is your tail, this entire thing is elevator. Okay. And the let me take this shaded region. Right, the moment produced by the shaded, dark shaded region will counter, actually the moment produced by, let me just take another color. Okay. Yeah, so the moment produced by the blue shaded area will compensate for the moment produced by the red shaded area, which in turn gives you delta E float to be 0. That is no moment. Okay. Okay. Now let's move on. Then we saw the stick conventions. Okay, pushing the stick forward gives you more velocity. How do you get more velocity? You reduce the CL. How do you reduce the CL? By reducing the angle of attack at the tail. Right? How do you reduce angle of attack at the tail? You deflect your elevator down. So pushing the stick forward gives you a downward elevator deflection, which gives you more velocity, less CL, less angle of attack at the tail. Okay, so this is the convention. Then we saw 3 cases where the delta E float equal to the delta E required, where the delta E float is less than the delta E required, and where it is greater. Okay. Now you must note that the delta E required is governed by the stick fixed static margin only, not by the stick free static margin. Right? What was delta E required? The amount of elevator deflection required to trim the aircraft at some given CL. Okay. Then this was the equation for the stick force. Okay. Hinge moment delta E by Ls into delta S. What is Ls and delta S? Delta E is the elevator deflection, HM is the hinge moment. What is Ls delta S? Can someone tell me? What is Ls delta S? So your stick is fixed at this point, right? And then you can push or pull the stick and it becomes something like this, right? So this length is Ls and the angle, how much it's deflected, is delta S. Alright? Okay. Move on. Then we saw the stick free and the stick fixed case. What were the differences? The only difference is in terms of the lift generated. Okay, so the lift generated in the stick free case is Cl alpha tail changes by this quantity. Okay, it's augmented by another quantity, which in turn gives you a new Cl alpha tail. That is the difference. That is what contributes towards the change in neutral point and everything. Okay, so there is a difference in the neutral point, stick fixed and stick free neutral point, that is given by this equation. There's also a change in the stability. Okay, so this is the stick fixed stability. This is negative, right? And this term is positive. Just look at it, look at each term. This is positive, this is positive, 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 positive. These two are less than 0, so this is also positive. So the entire term is positive. When we require DCM upon DCl to be negative, and more negative, more stable, less negative, less stable. So when this more negative quantity, to it you are adding a positive quantity. This is less than 0, this is greater than 0. So it makes the DCM upon DCl free less negative. That means the stick free stability is less than the stick fixed stability. Alright? Okay. So this is just a comparison between the stick fixed and the stick free case. The quantities under comparison are Cm at the Cg, Cm naught, DCM upon DCl, and x bar NP. This should be x bar. All of this should be bar, okay? Yeah. You can see the only difference is in Cl alpha. This is Cl alpha tail prime. So Cl alpha tail for stick free case. Okay, that is what contributes to all the differences. Here, here. Okay. Alright. Now let's look at the questions of week 12. The first question was, for a static stability level, that is slope of Cm versus Cl curve is minus 0.15 and the pitching moment at 0 lift is equal to 0.09, determine the trim lift coefficient. How do we go about doing this? You've submitted your answers, so how did you do it? How did you do this? How do you find Cl trim? They've given you Cm versus Cl, right? You have DCM, DCl equal to minus 0.15, correct? And they've given you pitching moment coefficient at 0 lift. So Cm at 0 lift is 0.09. They've asked you to find out Cl trim. How do you find this? So you take 2 points. One is where Cm is 0 and one is where Cl is 0. Okay? The Cl value where Cm is 0 is Cl trim. And this value you know is 0.09. So you take 2 points. Cm. Okay, so you take 2 points on the graph. One where Cm is 0, one where Cl is 0. So you take your Cm versus Cl graph like this. You take 2 points. One is this and one is this. You already know the slope. You take these 2 points and find out Cl trim. So here you have, so this is 0.1 and this is 0.2. At 0.1, what do you have? You have 0 Cl, Cl equal to 0 and Cm equal to 0.09. At 0.2, what do you have? Cl equal to Cl trim and Cm equal to 0. So you take 2 points and you have the slope of the equation. Try to find out Cl trim. You have 2 points, you have the slope, only one quantity is unknown, find it out. Find out and tell me the answer. Yeah, sorry about that. There was a network issue. Yeah, just tell me what is CL trim value from this data. You take the slope, that is dCm by dCl equals Cm2 minus Cm1 by Cl2 minus Cl1. Cm2 is 0, Cm1 is 0.09, Cl2 is Cl trim minus 0. Correct? Now you can find out CL trim. This value you know is minus 0.15. Can you find out CL trim from here? What is the value? Is minus 0.09 by minus 0.15. How much is this quantity? 0.06. That is the answer. Okay. Let's go to the next question. Again, the data, similar data is given where they're giving you slope Cm versus Cl, that is minus 0.25. So it's a stable aircraft, right? You require your Cm versus Cl to be negative. Okay. The pitching moment coefficient at 0, lift is equal to 0.09, and the center of gravity of the vehicle is located at x bar Cg is 0.3. They've asked you to find the stick fixed neutral point. Okay, how do you go about doing this? Similar ways. It's a very similar way. So they've given you dCm upon dCl, that is minus 0.25. They've given you Cm at 0 Cl, that is 0.09. They've given you x bar Cg is, how much is it? Yeah, so it is 0.3. Can you find out x bar Np? What quantity relates all these terms? What quantity relates all these terms? The static margin, right? What is static margin? It's negative of the slope. dCm by dCl is also equal to x bar Np minus x bar Cg. Okay, the only unknown quantity here is x bar Np. So what is the slope? Minus of minus 0.25, that's 0.25 is x bar np minus 0.3. So what is x bar np? What is the value? 0.25 plus 0.3. How much is it? 0.55. That is your answer. Okay, let's go to the next question. The contribution of the horizontal tail to pitching moment coefficient with respect to center of gravity of an air vehicle is given by. So they given you the equation cm of the tail, where alpha is the angle of attack of the air vehicle. This contribution of okay, what does this contribution of tail to air vehicle tell us? Given that the cm of the wing, they've given you cm variation of the tail and of the wing. So what does the contribution of tail to the vehicle tell us? So let's write down cm naught tail is 0.02, cm alpha of the tail is minus 0.2, cm naught of the wing is minus 0.02, and cm alpha of the wing is 0.001, right? So now look at these quantities and tell me what contribution does the tail have towards stability. Of these four quantities, which terms will contribute towards stability? Only the cm alphas, right? So just look at the cm alphas and tell me. Or find out the total cm of the aircraft. They've given you contribution of the tail and the wing separately. What is the total contribution? What is the total variation? What is the total equation? So what is the cm alpha of the entire aircraft? It's 0.2 plus 0.001. How much is this quantity? It is less than 0, right? It's less than 0. So the aircraft is longitudinally stable. Correct? Let's go on to the next question. Stick force gradient is a function of. We've done this question before. So just look at the stick force function formula. Okay, so this is the formula. Now look at the options given to you. So Fs was hinge moment into delta E by delta S LLS. Okay, now, hinge moment into delta E by delta S into LS. So stick force gradient, what does it depend on? Look at the options. It's none of those. It doesn't depend on any of it. Does not have lateral moment in the equation, does not have longitudinal moment, does not have directional moment. It has hinge moment. Okay. So it does not depend on any of these three. Next, for a heavily damped aircraft, one second, let me just erase this. Okay. For heavily damped aircraft, the aircraft response to an elevator will be. So of the two modes, which is the most dominant, short period or the phugoid, long period? It's a short period, right? That is, the frequency is high. So if the short period is activated, then the elevator deflection will cause the aircraft to respond rapidly if the frequency is high. Right? You can't just say rapidly. If the short period mode is dominant, then if the short period mode is activated, then okay. So it is rapidly if the frequency is high. Next, for a conventional aircraft, the sign of CL beta and CN beta are respectively. We just discussed this. Just try to get it on your own. Just try drawing it. Just take a positive beta and see if it produces positive or negative CL and CN moments. L is the rolling moment, N is the yawing moment. Okay, just try doing it. Just try doing it. Take a positive beta, see if the rolling moment and the yawing moment generated are positive or negative, and then you'll be able to get the signs of the two derivatives. So CL beta is negative and CN beta is positive, correct? This is the value. Answer. Next, when the center of gravity of the aircraft moves rearward, then the effect on short period mode will be. This question we had discussed, I think, in week 11, right? It's the same question. If this is the same question, you know the answer. Okay. Now, during flight, due to a passenger's movement, the CG of the airplane moves away from neutral point. Due to this, the elevator angle required to trim the airplane will be. It's a very tricky question. Just look at it. Again, this was a question that we had done before. Just look at it and tell me. Just take the Cm delta E equation and see if it depends upon the Cg somewhere. Does it depend on Cg, the Cm delta E equation? What was the Cm delta E equation? Did we have it in our slides? It is there in our slides, but I'm not sure if it's there in this revision slides. Is it? Yeah, here it is. Cm delta E is minus eta VHCl alpha tail into tau. So let's go write that. So Cm delta E is minus eta VHCl alpha tail into tau, right? So does any term here depend on the Cg? How do you define VH? Horizontal tail volume ratio. How is this defined? ST LT by SC. And what is LT? X bar AC of the tail minus X bar, it's not bar, okay, CG. You have an XCG here, right? So now you see if the CG moves away from the neutral point, will this LT increase or decrease? LT decreases, right? LT decreases. So Cm delta E decreases or increases? Cm delta E also decreases. Now the delta E required, the formula was what? Delta E naught plus X bar NP minus X bar Cg by Cm delta E into CL trim. I'm not sure about the sign, let's just go verify it. Yes, X bar NP minus X bar Cg, that is right. Yeah. So now can you tell me if the delta E required increases or decreases? Now that you know that Cm delta E decreases, so delta E required increases, right? Yes. Just write down the formula, see where the Cg comes into play. Now, if it did not feature in the equation anyway, it would not change. But now we know Xcg is coming in the equation here, right? So then you just analyze each term and then finally get to the delta E required equation, see if it increases or decreases. Okay, let's go to the next question. Okay, if only the horizontal tail contribution was considered for Cm alpha derivative, then how many times will Cm alpha become if tail length was increased by 2 times? So Cm alpha only horizontal tail, so horizontal tail contribution. Cm alpha is what? Minus eta Vh Cl alpha tail to 1 minus dou epsilon by dou alpha. Am I missing some term? No. Alright. So if the tail length was increased by 2 times, how will it affect? Does the tail length feature in this equation anywhere? So what is VH? ST LT by SC. What is ST? ST is the span of the tail, that is the length of the tail, right? So if I double the tail length, how much will Cm alpha change? That will also become 2 times, right? So this will also become twice. Do you understand? Okay. So ST is the length of the tail, span of the tail, correct? If I make that twice, Cm alpha will also become twice, correct? If I don't have wing contribution, they have mentioned that the horizontal tail contribution is the only thing that's considered, correct? So if I double the ST, my Cm alpha also becomes double. Okay. Next question. Keeping all the parameters constant, how many times will control derivative Cm delta E become if tail length was increased by 3 times? Again, take the formula for Cm delta E was what? Minus eta Vh tau, and what else was this? Cl alpha tail. Does the tail length feature in this equation? Just like the previous questions, just look at it, tell me. Just try doing it by yourself. Again, you have Vh is St Lt by Sc. If the St is increased by 3 times, Cm delta E will also become 3 times, right? Yes, I think with this we come to an end. Come to an end of our presentation, our session. If anybody has any questions, please do ask. You can also put it up on the forum. But if you have any questions right now, okay, if there are no other questions, if there are no questions, then we can end the session here. I hope you learned something from these sessions. I hope you were able to solve the questions easily. And I wish you all the very best for your exam. Do well, and thank you.